Hello and welcome back to this part 7 of our series on coordination chemistry. So today we're going to be looking at some of the complex examples or the consequences of crystal field theory, and as well as that, talking about Jahn-Teller distortions. So Jahn-Teller distortions, first of all, these are distortions wherein the proposed, or I guess assumed, octahedral structure of a particular complex is tetragonally distorted. So it means that if, for example, we had 6 identical ligands coordinated to a central metal, we would generally assume that each one of those ligand metal bonds would be the same length. But in Jahn-Teller distorted structures, we typically see that some of them are elongated, usually those along the z-axis of the complex. These sorts of distortions are particularly prevalent in things like copper complexes, copper 2 complexes, for example. So generally what's happening is that we're seeing this has a consequence where it distorts also the energies of the particular orbitals. So there is some form of tetragonal distortion brought about by the uneven occupancy of degenerate orbitals. So in this case, we see that the EG and T2G set are changed if from the octahedral case, we see an elongation of the ligands which are bonded along the z-axis. So the reason the z squared, the dz squared, of course, would be stabilized by the reduction in repulsive effect caused by the ligands interacting with the dz squared orbital being reduced, and the dxy as well would increase in energy somewhat because of what happens whenever these z-axis ligands are elongated. What happens is that typically the other 4 contract a little bit. And then on the other side, we can have a tetragonal distortion, which reduces the length of those bonds. That's also a Jahn-Teller effect. And so it has the opposite consequence. Any of the bonds along the z-axis or any of the orbitals along the z-axis, so for example, the dz squared, the dxz, and the dyz, those will all increase in energy as a result of this interaction. So generally, we don't see, or D2 is much greater than D1 in those situations. So most examples arise from the splitting of the T2G orbital. The effect is small but noticeable, and if the number of electrons in the dx squared minus y squared is not equal to the number in the dz squared, then significant distortion will be observed. And so let's have a look at a D9 copper 2 salt. So here we see that all of the orbitals are fully filled except the d squared minus y squared. And so this is the general structure of that salt. And so these are the bond lengths and how they change based on the different halogen, which is being the ligand. So other d electron systems, they require unsymmetrical occupancy of the EG set. So here we have D2. So what we see is that the T2G set is going to be fully filled, but then we have unsymmetrical occupancy of the EG set here, so the dz squared and the dx squared minus y squared, and typically see examples of that being cobalt 2 plus and nickel 3 plus. Then the D4 case, we see that we have symmetrical occupancy of the T2G set, but in the EG set, it's unsymmetrical. So copper 2 plus, typically D9. So this is an octahedral complex, but there's unequal population of the EG orbitals, which results in a distortion of some of the bonds. So it's tetragonally distorted. 2 electrons decrease in energy and 1 increases. And this generally makes it more stable than an octahedral complex would otherwise be, because in a way it never really was an octahedral complex. Did it start off as an octahedral complex and then become something different, or was it never actually octahedral to begin with? And can it sort of be shown as on its way to a D8 square planar? Because remember, in the case of a square planar, it's typically quite similar to octahedral complex. However, what we're seeing is that there's going to be obviously the loss of any ligands along the z-axis. So other cases, so we have an octahedral D4, which is often tetragonally distorted. Same reason for this is as the D9 case. This is chromium 2 plus and manganese 3 plus. So we have generally symmetrical occupation of the D2G set, but the EG set is asymmetrically filled because one of the orbitals has an electron and the other does not. Okay, so some consequences of crystal field stabilization energy. We can see the hydration energy of various metal salts with their change in atomic number. So as we go across the periodic table, we see the hydration energies change. And this can be kind of sort of observed that there's more energy being released during the hydration than we might expect. But in the end, if we correct for the crystal field stabilization energy of each of the different metals, then we see a smooth curve being observed. So we have, for example, here a great reduction going from calcium 2 plus down to titanium 2 plus, vanadium 2 plus, chromium 2 plus. Each time we're adding another electron. But if we correct for the crystal field stabilization energy, which is making these obviously more stable as we go along, and then manganese here, that's going to be the one which is not really needing any corrections, and that's because of its d electron count, which sort of will result in it having the same hydration energy, corrected or not. Whereas the same thing is seen for zinc 2 plus. Zinc 2 plus and manganese 2 plus both lack any kind of crystal field stabilization energy. Manganese, because in this case with the water ligand, it's a high spin complex. So we've got 3 electrons in the T2G set and 2 electrons in the EG set, giving us 0 for the crystal field stabilization energy. Then for the zinc 2 plus, it's going to have 10 d electrons. So each one of the orbitals is fully occupied. Again, also meaning that we don't have any crystal field stabilization energy for those two. So this gap here, this correction will correspond to about 0.8 delta O crystal field stabilization energy. So this is what we would see for the vanadium 2 plus. And then, of course, this one is 0 delta O, which is crystal field energy high spin. Lattice energy, similar things are seen. Similar results area observed in the lattice energies for the dichlorides across the first period. Note that the cation is an octahedral coordination geometry in the solid lattice. So even though these are, titanium dichloride, vanadium dichloride, chromium dichloride, they're actually coordinated to 6 chlorides within the lattice. It's just for every chromium, there's going to be 2 chlorines. Then for the ionic radii, again, we see similar trends whenever we take a look at comparing the ionic radius to the crystal field stabilization energy. We see the same sort of anomalies. So in octahedral divalent 2 plus, first row transition metals, calcium 2 plus, manganese 2 plus, and zinc 2 plus lie on a smooth curve. They have no crystal field stabilization energy. However, the others are smaller than they should be because of this crystal field stabilization energy. So the consequences of crystal field stabilization energy. Generally, transition metal complexes are more stable than they should be, and this can be directly related to the crystal field stabilization energy. It's a stabilizing force. And so we relate this to 3 measurable properties. The hydration energy, so how much energy does it take to form the hydrated complex? Lattice energies, how much energy does it take to form an octahedral lattice? Ionic radii, how large are the ions in an octahedral lattice, which is related to the bond length. And then melting point of the metals, we get data and do it for yourselves. So you can count also the d electrons. So I encourage you to go out, get some melting points of the various metals, and then compare it to what their crystal field stabilization energy may be. Okay, so let's have a look again at the splitting of d orbital energies in octahedral complexes. So how does the ligand field influence the energy of the 5 metal d orbitals? So if there's orientation along the ligand metal bond axis, that's the two orbitals that we particularly see increasing in energy, which in the octahedral complexes form the EG set. These orbitals are the dz squared and the dx squared minus y squared. Then if there's orientation between the metal ligand bond axis, these orbitals are the dxy, dxz, and dyz. Here's the splitting again that we've seen previously. So we have the metal gas phase cation, and a spherical negative charge distributed uniformly in a sphere across the metal. Then we can see what happens when we isolate the negative charges on each one. And then if we consider the actual electrostatic attractions, positive being attracted to negative, we see that there is also a correction for that. And that's sort of moving towards this idea of considering the ligands properly rather than just negative point charges. So generally, this is how we would draw an octahedral complex splitting diagram. Electronic spectra, studies of electronic spectra of metal complexes provide information about the structure and bonding present there. So absorptions arise from transitions between electronic energy levels, so transitions between metal-centered orbitals possessing D character. So it's D to D transitions. So these are generally weak intensity because of their Laporte forbidden nature, like quantum chemistry does not allow it. So these transitions are usually seen in metal complexes. And they can also, however, be transitions which are between the metal and the ligand-centered orbitals. And so these are metal to ligand or ligand to metal charge transfer transitions. So these are MLCTs or LMCTs. And these are typically having strong intensity. That's because we have transitions between different principal quantum numbers, which is allowed. So absorption bands are usually broad due to vibrational and rotational levels. So, we don't just have the electronic transitions, but we also have the vibrations and the rotations within that. And of course, this absorbance can be related to the epsilon max times C times L, which is ultimately the Beer-Lambert law. So what we're measuring during this is going to be the transition from, if it's in this D1 complex, the transition from the T2G set up to the EG set. And so the transition between those is going to be given as the delta O. And so we can measure this using UV-Vis spectroscopy. So on the irradiation with light at frequency N, which is equal to this delta O over H, an electron is transferred to one of the higher energy EG orbitals. And so that energy corresponds to a particular wavelength. So the field splitting energy, delta O, can be determined from spectroscopic data, obviously, because that transition is an absorption which can be recorded at a particular lambda max. And that, of course, can be fed back into the energy. So for different complexes of titanium-3, we can get different splitting energies, and that can tell us a lot about the influence of the ligand on the metal center and especially on its d orbital energies. So titanium-3 is a D1 complex and exhibits one transition or one absorption transition because it only has one electron in its electronic spectrum due to the transition of the electron from the T2G orbitals to the EG orbitals. The energy of the absorption corresponds to this delta O, and we can see that if we have a bromide going through to cyanide, so this is sort of going from what we have weak field ligands, so these are high spin complexes, up to strong field ligands, which are going to be low spin complexes. We can see that the low spin complexes, as we would expect, have a much larger splitting energy. So the D to D transition or the D to D absorption bands of transition metals involve redistribution of electrons that are localized on the metal. There are also electronic transitions in which an electron moves from a ligand-based orbital to a metal-based orbital or vice versa. And these absorption bands are generally very intense. So a ligand metal charge transfer band involves the movement of an electron from a ligand to a metal. And so for an example, you would see there is like this iron complex with its thiocyanate and its water ligands, and that's typically a red complex. And the opposite is whenever we have a metal with a lot of electrons and something which can accept electrons, so like maybe that's an aromatic type of ligand, So an MLCT is a metal ligand charge transfer band. And so this is where the electron moves from the metal to the ligand. And an example of that would be like a copper phenanthroline complex. So the phenanthroline is aromatic. It can kind of accept momentarily those electrons. And the copper, obviously copper 1 is very electron rich. So the magnitude of the splitting energy is dependent on a number of things: the charge in the metal, the oxidation state. This obviously changes a lot for the first row transition elements. And it varies from about 7,500 wave numbers to about 12,500 wave numbers for divalent ions, and from about 14,000 to 25,000 for trivalent ions. The position in the group also changes, so values for analogous complexes of metal ions in a group increases by 25% to 50%, going from one transition series to the next. So here we have cobalt, rhodium, and iridium, which are all in the same group. We can see that the biggest jump is from the first to the second row. For the second to the third row, there's not such a significant jump. And that's something we see in a lot of the properties of transition metal complexes, is that if they're from the same series, then we're going to see the biggest difference between the first row and the second row, but the second and third rows are going to be a little bit similar to each other. Geometry and coordination number also will affect the magnitude of the splitting energy. So for identical or nearly identical ligands, the delta T, or the tetrahedral splitting energy, is about 4/9 of the octahedral splitting energy. So if we're able to find the octahedral splitting energy, then we can also apply that to the tetrahedral. So this is a result of the reduced number of ligands and the orientation relative to the d orbitals. And that sort of means that there's not as much energetic either stabilization or destabilization. And so the energy ordering of the orbitals is reversed in tetrahedral complexes relative to that in octahedral complexes. And that's because of the way that the orbitals, which orbitals are interacting with the ligands, changes. And then, of course, the identity of the ligand is also important, because the dependence of the splitting energy on the nature of the ligand follows an empirical order known as the spectrochemical series for all metals in all oxidation states and geometries. So the order of ligand field strength with increasing dq, which is the sort of splitting energy. So we have going from cyanide, which would have the most effect, all the way through diiodide having the least. And so note that water has a larger effect than hydroxide, and this can't really be explained in terms of the electrostatic model, and it needs to be explained in other ways, which we will get onto in the next part. So the order of metals with increasing dq, or splitting energy, you see that goes from manganese, so from 2+ ions through to 3+ and then 4+. And then the splitting energy increases with increasing oxidation number, and the splitting energy increases going down the group. So these splitting energies can be estimated. They were estimated based on sort of the empirical data that was capable of being obtained at the time. And so it was found that 10 times dq is approximately equal to F times G, where F is the ligand F factor and G is the metal G factor. And so we multiply these two together and then times it by 1000 wave numbers, and we can estimate the splitting energy. And so we're asked to do two examples here to estimate the splitting energy for a delta octahedral for the following octahedral complexes: a chromium ammonia complex. So the chromium, if we look back at our table, chromium 3+, so chromium 3 is 17.4 G factor, and then ammonia has an F factor of 1.25. So we then calculate those, we fill it in. So 17.4 times 1.25 will give us a deltahedral splitting estimation of 21.75 times 10 to the 3, or 21,750 wave numbers, which is remarkably close to the experimental value. Then for cobalt 1, ethylene 1,2-diamine. So ene is 1.28 for its F factor, and cobalt 1 is not here, but we can find it in tables of data. So, or sorry, it should be cobalt 3 is 18.2 times 1.28. Multiply those together, and we see that they're very close to each other as well. Okay, so that'll do us for this part, and then we go on to the next part in the next series.